This is a video looking at the so-called exact values of the trig function sine, cos and tan for these three particular angles, 30 degrees, 45 degrees and 60 degrees. When we talk about exact values, what we mean is not a truncated or rounded or infinitely long decimal value, which is what mostly you'll get from your calculators. But this is exact in the sense of giving you actually a whole number in one particular case, or an exact fraction or a surd. Being further pure mathematicians, we like to be as exact with these things as possible, and of course rounded or truncated or infinitely long decimal number will never be as exact as its surd equivalent or a fraction, if that's the case. So you can see that I've got two triangles on my screen there, one which we'll be using to look at our 45 degree case, and a second one which will need a little adjustment but is the basis for looking at our 30 degree and 60 degree cases. Of course, we ought to be thinking in terms of radians as well, equally just as much really as in degrees, if not a little bit more. So of course 45 degrees, instead of 45 degrees we could be talking about pi over 4 radians, and instead of 30 degrees we could be thinking about pi over 6 radians, and instead of 60 degrees we could be thinking about pi over 3 radians. So having a look at these two triangles, the top one first, the 45 degrees or pi over 4 radians, we're looking at a right angled triangle here, with right angle on my diagram down in the bottom left hand corner. And of course to get a 45 degree angle there, that leaves us with 45 degrees for the other one as well, and that means that this must therefore be an isosceles right angled triangle with the two sides on either side of the right angle being the same length as each other. I'm going to choose to have a length of 1 unit, 1 centimetre, 1 metre, whatever you like it to be, one something along those two sides. And then a quick little bit of Pythagoras. 1 squared plus 1 squared gives me 2. Square root that gives me root 2 on the hypotenuse of this triangle. Now a word about the size of the triangle, why I'm choosing to have 1 and 1 and root 2 there. Actually the choice of the length there to have is entirely arbitrary. Any right-angled isosceles triangle with 45 degrees, it will have to have 45 degrees in the other two angles if it's right angle and isosceles. And of course that means that any other size, apart from the one that I've got on the screen there, would just be mathematically similar, i.e. an enlargement or reduction of the triangle that you can see there. And once we get to working out the trig ratio values for these things, the similarity, the scale factor change to the size would cancel out. So actually the choice of size is arbitrary. We can choose any length we want. We could have 2 and 2, and then we'd have 2 root 2 along the hypotenuse, or any other length you choose to have, and it wouldn't matter because the trig values would come out the same anyway. So if we have a look at the three ratios for that top triangle, obviously sine of 45 degrees, I'm going to use the bottom right hand angle as my angle of focus for these things here, but it wouldn't matter obviously because they're both the same. So if we think about sine of 45 degrees, we can see straight away from that sine of 45 degrees, which obviously would be the same as the sine of pi over 4 radians as well. And just as the sine definition, opposite over hypotenuse, opposite we've got 1, hypotenuse we've got root 2, so just 1 over root 2. And of course you might want to have that, sometimes people just leave it like 1 over root 2 and that's absolutely fine depending on the situation, what you're doing with it and everything, but you might want to rationalise the denominator on that one, and that obviously would end up as root 2 over 2. So there we've got an exact value for that. Cos of 45, well, since the opposite and adjacent sides are the same, it makes no difference. So cos of 45 or cos of pi over 4, if you're working in radians, adjacent over hypotenuse will give us 1 over root 2 as well, or root 2 over 2 if we want it with a rationalised denominator. And then last one to think about there clearly is the tan of 45 degrees, or tan of pi over 4 radians. So tan being opposite over adjacent, so we just got 1 over 1 there, or just 1. And there's our exact values for 45 degrees for each of the 3 trig functions. So on to our second triangle, and in our second triangle we're interested in 30 degrees or pi over 6 radians and 60 degrees or pi over 3 radians. And what I want to do with this, so what I've got here is an equilateral triangle, and I'm going to choose with a similar argument about the actual size. The actual size is not relevant. I can choose any numbers I want. Because this is an equilateral triangle, it will have 60 degrees in all of its 3 corners. And I'm going to choose to have a size of length 2 along each side. I'll just label up one of them because I want to make a small change to this triangle by adding in a straight line, because what we're interested in really here, of course, is right angled triangles. So if I just drop a perpendicular straight line from the top vertex down to the bottom there, that's going to give me 2 benefits. Firstly, it's going to give me the right angled triangle down at the bottom, the right angle down at the bottom. Oops. But also, rather fortunately, it's going to give me a 30 degree angle in here, so I can use this one triangle. So I'm just going to be using the left hand side. In this case it could have been the right hand side, but I've chosen to use the left hand side of the full equilateral triangle. So I'm actually going to ignore the right hand side here completely. Oops. I'm not going to be interested in this side of it at all. So I'm just looking at the left hand half. So I've dropped a perpendicular here. I've got a right angle down at the bottom. I've got 60 degrees in the bottom left. I've got 30 degrees in the top corner. I've got a length of 2, and now since I've bisected that base of the original equilateral triangle by splitting that angle at the top in half, I've also then bisected, split in half, the base of the triangle, and that means that this has a length of 1 down at the bottom here. And now I can use my Pythagoras to work out the length of that perpendicular as well. So I've got 2 squared on the hypotenuse, 2 on the hypotenuse, so 2 squared, take away 1 squared along the bottom there, gives me 3. So therefore the length of the perpendicular here must be root 3. Sorry, that's not a very good 3. I might just try and do that a little bit better. So we've got a length of root 3 on the perpendicular there. So we've got 2 on the hypotenuse, a base length of 1, and a vertical height of root 3. And once I've got those things in place, I'm now in a position to look at the sine of 30 degrees. which obviously is the same as the sine of pi over 6 radians. So I'm focusing on my 30-degree angle here and looking for the opposite and hypotenuse, opposite being length of 1, hypotenuse being a length of 2, so I've got a trig ratio of 1/2 for the sine of 30 degrees or pi over 6 radians. Then we can look at the cos of 30 degrees. And clearly that's going to be the same as the cos of pi over 6 radians. And this time, with my focus at the 30-degree angle, I'm looking at adjacent and hypotenuse. So adjacent root 3, hypotenuse 2, gives me a third value of cos of 30 degrees being root 3 over 2, or cos of 6 pi over 6 radians. And then we can have a look at the tan function. So we've got tan of 30 degrees, or tan of pi over 6 radians if you prefer. So here we're looking, with our focus on the 30 degrees, we're looking at opposite over adjacent. So 1 is our opposite side, root 3 is our adjacent side, 1 over root 3. And you might want to, as again with the 45-degree ones, we might want to rationalise that. Sometimes you'll leave it as 1 over root 3, but you might want to rationalise the denominator there and make that root 3 over 3. And so there's our 30-degree angle exact values. Now if we switch our focus to the bottom corner, the 60-degree corner, and we have a look at, actually I'm going to switch the order of these round, the trig functions around. I'm going to put the cos one first, and hopefully it'll be obvious in a second why. If I think about the cos of 60 degrees, which of course is the same as the cos of pi over 3 radians. So now focusing my attention on the 60 degrees, for the cos I want adjacent over hypotenuse, 1 over 2. And that's why I wanted to put it there, because obviously it's the same as the sine of 30 degrees. And similar job going on here. If I think about the sine of 60 degrees, which clearly is going to be the same as the sine of pi over 3 radians. This time, focusing on the 60, I'm looking at adjacent over hypotenuse. Sine. I'm looking at opposite over hypotenuse, root 3 over 2, and of course that's going to be the same as our cos of 30. And finally, with our tan. So tan of 60 degrees, same as tan of pi over 3 radians. So we're looking now at opposite over hypotenuse, so that's, opposite over adjacent, root 3 over 1, or just root 3. The business about the sines and coses, sine of 30 being the same as cos of 60 and cos of 30 being the same as sine of 60, just illustrating the fact there that if we have two angles which add up to 90 degrees, then the sine of one of them will be the same as the cos of the other one, and I just wanted to illustrate that point there. So there we have it. We have exact values in fraction, whole number or surd form for the three basic trig ratios for the angles 30 degrees, 45 degrees and 60 degrees, and little diagrams to help us remember which is which.